So why do we use this method, so-called conjugate gradient? Okay, I have different notes from different years. Okay. At the beginning, I always want to define so-called conjugate gradient. Okay, it's a new idea. So let's think about Newton's method or steepest descent. We have our current design. For steepest descent, we find the negative gradient direction. We will use the alpha search, the line search, to determine how far do we move. But we stick with that particular direction. For Newton's method, we also compute the negative gradient. But in front of it, we have a pre-multiplier, which is the inverse Hessian. So inverse Hessian is very powerful. It will change the direction of this moving direction and also change the length of the vector. And because it was derived directly from second order Taylor expansion, so the inverse Hessian knows how much movement you need along this new direction. So Hessian matrix has a lot of useful knowledge, but we don't want to use it during the iteration. So today, we are going to introduce Hessian in this methodology. However, once we put it in our methodology, we will try to use multiple concepts to redescribe the equation, basically reformulate the equation. Try to change the form of the equation into newer forms until we no longer need to calculate the Hessian. So it's very interesting approach. So here, let's define so-called conjugate gradient. So when we say conjugate gradient, conjugate direction, it doesn't have to be the Hessian matrix. It could be any symmetric matrix Q. So we will have two vectors, D1 and D2. They are not the same vectors. They are pointing at different directions, at different lengths. And they may not be orthogonal to each other, so not perpendicular. Okay? But if we introduce this Q matrix in its calculation in the following way. If D1 dot Q dot D2 equals to 0, we can say these two directional vectors are Q orthogonal. After so-called the Q transformation, they become orthogonal. Okay, so if you look at D1 dot Q dot D2 and focus on Q dot D2, Q basically is like a transformation. Imagine you are learning kinematics. You have a rotational matrix pre-multiply a vector. The rotational matrix basically transforms this direction vector to some other newer vectors. So Q is like a Q transformation on top of D2. After the transformation, D1 and the resultant vector, the dot product of them, equals to 0. So D2 is perpendicular to D1 after the Q transformation. Then we call this kind of relationship as Q orthogonal. And we say they are conjugated with each other because of this Q transformation. Okay, so we're going to do a bunch of these in the following derivations. And later on, Q will be the Hessian matrix. Because we know when we transform our gradient by the Hessian, it kind of turns our moving direction toward the good direction, and also define its length to the proper step size. Okay, but in general, conjugate directions doesn't need to be using the Hessian matrix. So this is more like a general definition. Okay. So now, if you look at, this is basically what I was trying to explain. If your objective function looks like the contour looks like a circular shape, then the steepest descent direction basically point to the center. That helps you to find the solution so easily. But when you have a objective function like this, then the contour of your function looks like ellipse. Then when you compute for the gradient, it doesn't point to the center. That's why steepest descent direction, steepest descent method will be moving like a zigzag. So if you can transform the space from ellipse to circular, then your moving direction can go to the center more easily. That's why the conjugate gradient method is trying to do some kind of transformation. Okay, basically the Q of orthogonal transformation. Now we will start our derivations. So before I do that, basically say the same thing every time. Okay. Let me see which one goes first. Okay, I think I will use this one. Let me make sure. Let me just stick with one of them. Okay. So let's go to the definition of second order Taylor expansion. So any function can be approximated as a approximation of f, and it could be written as, so basically this is k means you plug in the k value, right? Plus, now is a multivariate form, so in the vector space. So you have a vector x minus the current point, dot product with the gradient, plug in the current value, plus 1/2. Same term here, dot product, agent, and plug in the current value, dot product. So basically this is second order Taylor expansion. And what I'm trying to emphasize is that whenever you plug in the k variable, xk, everything with a k is a constant. So the highlighted part by the red color are just a constant. So the only variables are the x, right? Okay. Now since here basically just a definition. What is sk? Basically with a k, that means you plug in plug in the k value. Now we are going to call this, I think, call equation 0. This is just later on we may use it. So this is equation 0. Now there's the equation 1. Equation 1 is the derivative of equation 0. But since this is multivariate, so when you do first order derivative, you are basically operating the partial derivative. Then it turns out you will have a gradient vector. So this is, you're doing the gradient operation. So when you do that, okay, here's the variable. So you don't care about the constant terms because after derivative they are gone. So the gradient f and times x, first order derivative, only the coefficient is left. That's why there is a gradient fk like here. Now, because there are two variables, you are going to perform first order derivative twice and sum them up. When you do the first one, the first term disappears, then it's a result of Hessian dot product with a remainder right here. And the other gradient basically removes the right hand side, and then same thing, Hessian dot product with the first one. And last time we used the Einstein's summation convention to show you that the result is basically Hessian times a dot product with x minus sk. Okay, because there are two terms, so multiplying 1/2. At the end, the coefficient equals to 1. Okay, so this can be seen last time when we derived the first order derivative in Newton's method with multivariate function. So we did that already. We call this one equation 1. Now, in Stephenson, we know we would like to move our design point toward a new direction. Okay, so this is the current design. We are also in conjugate gradient. We are going to move toward decay, some moving direction. But at the beginning, we are basically doing just like Stephenson. We will be moving toward the Stephenson direction because in the first iteration, we don't have too much information, not enough information. But later on, from the second iteration, we're going to do gradient again, and then we had the gradient information from the previous iteration. We're going to use both of the gradient, the current one and the previous one, combine them together in order to determine what is the new direction, following the conjugate direction approach. Okay? So, and in both, no matter what dk we use, we still need to evaluate the step size. So alpha still needs to be computed for the entire process. So the line search is still there. The line search is still there. But for conjugate gradient method, what's new is that we figure out a way to improve our moving direction. In Stephenson, we will do the zigzagging, right? Every time we turn 90 degrees. But for conjugate gradient, the first time still following the negative gradient, but for the second iteration, we will no longer do the 90-degree turn. Today's lecture will tell you, okay, you should update this moving direction based on some knowledge, and we can do a better job. Okay, so conjugate gradient only improves decay, but still require alpha k calculation. Okay, so right here, let me see. So we will define this decay in the starting from the second iteration. We will not only use the gradient in the current iteration, we will also update in such a way. So basically, this is like we propose to do it, but we don't know how those values are. Okay, so we decide we not only move toward the negative gradient, we will move also plus the previous decay. But in front of the previous decay, we will have a pre-multiplier, so-called beta. And beta is to be computed. And let's propose to do that and see how we can find a grade beta. So dk can be updated. Okay, so later on we are going to determine how to compute this beta. Okay? So this is called equation 2. So now we have equation 0, which is the second order Taylor expansion. Equation 1, which is the gradient of 0. Equation 2, basically very similar term of steepest descent, basically linear searching equation. But inside the decay, only in the first iteration we will follow steepest descent. Starting from the second iteration, we can do this. So this is very new. This is the new equation. Equation number 3 is the new one. We will check gradient, negative gradient, and then we also move toward the previous decay direction with a pre-multiplier, beta. Okay? Now, so from here, from this equation, we are calling this as a 3. We can derive this as a 3 prime. So this one is, this works for all iterations, right? So even when I upgrade my iteration number by 1, the equation is still valid. So if this is right, then originally this is dk. So for dk plus 1, the following equation should be valid. So just plus 1 to all the index. Then you have a dk plus 1, negative gradient k plus 1. Here is beta k and dk. So from here you can see the index is very important. Otherwise you will be making mistakes later on. Okay. So this equation basically is telling us in the next iteration dk plus 1 is going to look like this. Okay? Now, we're going to make one assumption. We want certain things to happen. So later on something magical will happen. So we assume we want every time when we move, we want all the dk's to be hk orthogonal. So so-called earlier we mentioned q orthogonal, right? But this time we are going to make this happen. We want all the dk to be hk orthogonal. So they are conjugated with the hk transformation. That's if we want this to be happening, then let's see what's gonna happen. So everything starts with this concept. We want this, and then we will later on use those to derive beta. So it's like what would be beta b so that dk and dk plus 1 would be hk orthogonal. So the following derivation basically gives you this kind of answer. Now, so since dk and dk plus 1 are hk orthogonal, so earlier we already know dk dot hk dot dk minus 1 must be 0. So after transforming dk minus 1 by hk, these two vectors are perpendicular. So that's why they equal. Okay? And we can also say, okay, now dk is conjugate with dk minus 1. Okay? So, if this is happening, the current dk is hk orthogonal with the previous dk. Then, how about the next one? So we also want dk to be hk orthogonal to the next dk. Okay. So if this is happening, then dk dot hk dot dk plus 1, we want this to be 0. Okay, so this is equation 4 and this is equation 4 prime. Okay. But you might, if you are careful, then you might ask, don't we need hk right here to be hk plus 1? So I would say, if you do that, the later derivation won't work. You will miss one index. So what I believe is this derivation relies on both h orthogonal between the current dk and the previous dk and the next dk. So it's a hk orthogonal relationship between the current one and the previous one and the next one. We need that. That's why it's derived in this way. And basically, I don't invent this method. I'm not the founder. But it turns out this is what the method needs. Okay, so if you let's just believe it at this point, then accept there's an equation 4 and equation 4 prime. Later on we need them. Okay, now this is equation 0. Okay, not Chinese character. Just because you know, if you use a circle and a 0 inside, then you don't know what that is about. That's why I draw a square. So from equation 0, here, from equation 0, I basically rewrote this entire equation 0. However, this time I put some index here. So let's make a comparison. Equation 0 was here. See, for the function right here and the variable right here, I didn't put an index. So now, if the variable is for the next iteration, then x would be xk plus 1. So function f would be function f at the k plus 1 iteration. That's why right here you would have fk plus 1 equals to s, fk plus xk minus plus 1 minus sk, and so on. Okay, basically just plugging in xk plus 1 into equation 0. Okay? Once you have that, take a look at the terms I am highlighting in this equation and check equation 2. There's an equation 2 right here. You notice that xk k plus 1 minus sk equals to alpha dk, right? So we can replace those terms by alpha dk. That's why you end up with these. There's an alpha dk here, replacing this guy. There's an alpha dk, another alpha dk. Alpha is a scalar. So when you do this, both alpha k can be put together. That's why you have an alpha k squared. And the remainder will be dk dot hk dot dk. Okay? So once you plug in that, what does Newton's method tell us? Whenever you have a second order Taylor expansion, if you take first order derivative and if it equals to 0, that's where the minimum is. So we want to have gradient of f k plus 1 equals to 0. So let's do gradient of f k plus 1. But now there's an interesting thing that is happening, is that since we define the xk plus 1 with an introduction of new variable, which is alpha, which is unknown right now. So whenever this is happening, the gradient f equals to 0, we also need to do partial derivative with respect to alpha. And that has to equals to 0 as well. That's a new variable. So let's take a look at the partial derivative of fk plus 1 with respect to alpha k. Okay, so basically doing this whole thing with respect to the alpha k. So let's now focus on alpha k. Fk is a constant, disappear. There is an alpha k, so the coefficient, we got the coefficient, so basically here's the coefficient. So that's why you have dk dot the gradient fk, right? And right here you have alpha k squared, so first order derivative, you will have 2 times alpha k. So the 2 and the 1 have balance out. So the coefficient equals to 1 right here. And the remainder will be the alpha k and also the rest of the coefficient. And you want this to equals to 0. Okay? So once this is happening, you can rewrite the whole thing. You realize there is a pre-multiplier of dk. Pre-multiplier of dk. Alpha k is just a constant, just a number. So it can be anywhere. So the pre-multiplier of dk can be take out, and then the right hand side of everything can be put inside a bracket. So right here you have a gradient of fk plus alpha k times hk dot dk. Right here. Okay? Then what? Then not yet. Then not yet the right hand side. You need to do something here to prove something. So not yet the right hand side. So once we have this equation, we need to check on equation 1 and 2. Equation 1 and 2. So equation 1 is this guy, the first order derivative of the second order Taylor expansion. And equation 2, basically the xk and the line search equation. So from 1 and 2, what do? We plug in 2 into 1. And then, yes, basically we're plugging. That's for the first one, you plug in xk plus 1. So that's why you have fk plus 1 and xk plus 1. And then the equation 2 tells you this guy is alpha k. So gradient, this equals to gradient fk plus alpha hk dot dk, right? And you found this one is exactly this one, completely the same. That's why dk dot this guy, gradient fk plus 1 equals to 0. So it gives you equation 5, which will be useful later on. So when I learn this course, learn about conjugate gradient, I just follow, okay, do this, do that. Why do we do this? No idea. Okay, this is what, I know what you are feeling right now. Okay, why do we do this? Because just follow the procedure. And okay, every step makes sense. Just plug in here and there, and then do this, do that. And later on you will see something magical. I feel like conjugate gradient is very magical. Okay, so now we have equation 5. Okay, here. Let me see. Already here. Okay. So now, starting from a different thing again. So we had 3 prime. 3 prime is the equation that is have a term of beta. So basically the new direction conjugate gradient method wants to move along the dk plus 1, but we have no idea what beta is yet. So now we will have post multiply of hk dot dk. So basically, this whole thing dot hk dk, and let's see what's gonna happen. So dk plus 1 dot hk dk. If we do that, the right hand side needs to do dot product with hk dk as well. So you have negative gradient dot hk dk, and also beta dk dot hk dk. Okay, and here I think the inventor or the mathematician intentionally is trying to make the left hand side equal to 0. Remember that when we assume the current D and the next D is H orthogonal, then this must be 0, right? So that means the sum of the right hand side must equal to 0. Okay, great. Now we can read the we can do some math and then figure out what is beta k. Because earlier, what's the goal? We have no idea what beta k is. So the goal is to find a proper equation of beta k so the dk's are H orthogonal. Now is the opportunity. So here we have a term right here. If you have a vector dot product with another vector, basically it's a number, it's a value, it's a scalar. Vector dot product with another vector, it's a scalar. So this whole thing underlined with the red line is a scalar, and the term right here also a scalar. Then you can divide by the term right here. So you can derive basically beta k is this particular first term moved to the left hand side, and the right this another term also moved to the left hand side. So you derive the beta k. This is basically gradient f k plus 1 dot hk dot dk over dk dot hk dot dk. Can we already do optimization right here? Yes, we can. So if you directly use this, this will directly improve your moving direction. However, you are still computing hk. Then why bother? Just use Newton's method. So at this point, we now figure out what's the value of beta k. So all the dk's are hk orthogonal. But for the calculation of beta k, we still need hk, Hagen. So can we rewrite beta k in a certain way so we no longer need to compute for Hagen? So that's what we're going to do next. Now, let's take a look at the upper part of beta k. So we're going to handle the upper part and the lower part one by one. Now let's handle the upper part. So the upper part is gradient f k plus 1 dot hk dot dk, okay? So here, what are we going to do? We are going to take a look at the dk. What is dk? So dk can be found from equation 2, right here. When we firstly define dk, basically it's the line search, xk plus alpha dk. So dk basically equals to xk plus 1 minus sk divided by alpha k. That would be dk. So that's why you have a term right here. This is basically dk. Okay? And once you have this, and notice that I have you have a new term right here. Not new term. You end up with a term right here. hk dot product with the upper part right here. So what is that guy? We can go to equation 1. Equation 1 basically is the derivative of second order Taylor expansion. And inside the derivative of the gradient fk, you have hk dot x minus sk. That's basically this guy. So it basically is telling you this term can be replaced by gradient f k plus 1 minus gradient fk. So that's why you have the term right here. The k plus 1 gradient minus the current gradient. Up to here, did you see something interesting? The calculation of Hagen disappeared. We were handling the upper part. We just applied whatever equation that we had earlier, just plug in, and then it turns out you can compute in such a way so that you don't need to calculate Hagen. Okay, so let's continue to handle this equation. Basically, plug in, because this is a dot product. Basically, plug in. So we have a gradient f k plus 1 dot, gradient f k plus 1 minus, gradient f k plus 1 dot, gradient f k over alpha k. So now we are going to call this equation 7. And the equation 7, in here, we're going to handle this pink area, this pink term. Okay? So this is the pink term. We're going to do something with the pink term. So the pink term is gradient f k plus 1 dot gradient f k. So what is gradient f k? Can be written as from equation 3. I told you. Gradient f k can be written as beta k minus 1 d k minus 1 minus dk. Okay? This is from equation 3. Equation 3 is here. So once you do that, you now it's a dot product. So just expand the terms. You have a negative. You have negative sign. Gradient f k plus 1 dot dk. Okay, and then plus coefficient beta k plus 1. Gradient f k plus 1 dot d k minus 1. Here, because of equation 5, this is 0. So let's go back to equation 5. It's right here. So now we know why this is important, because we are going to make some of the terms in the later derivation 0, right? So current moving direction dot product with the next gradient equals to 0. Okay? So go back to where it is here. Current moving direction dot product with the next gradient equals to 0 because of equation 5. Okay, so this pink term now only have beta k minus 1 times gradient f k plus 1 dot dk minus 1. We're going to call this equation 8. Well, then what do we handle equation 8? In order to derive further, we need to do something with the equation 8. This remainder. So there's the equation 6. It's basically the equation 6 is right here. It tells you combining 1 and 2, you have equation 6. The gradient f k plus 1 equals to gradient f plus alpha hk. Alpha hk. Alpha hd. Alpha hd. So let's go to here from equation 6. See, gradient f k plus 1 equals to gradient f k plus alpha hd. Okay, so if there's an equation 6, so this term can plug in to replace the term right here, because we know the next gradient equals to this term. So just plug in. So once you plug in, you have a bunch of equations right here. You have a beta k minus 1. This is what you plug in. Dot product with d k minus 1. So just expand everything. So beta k minus 1 gradient f dot dk minus 1 plus you have alpha k beta. I think this is typo. This should be beta k minus 1, but it doesn't matter. It's a typo. I will correct it. Minus 1. Should be beta k minus 1. But it doesn't matter. Because later on everything is 0. So here you have so notice that this is a one vector dot product with another vector, but the first vector has a matrix in front of it, and you can only reverse the order when and write everything like this if this matrix is symmetric and gradation is symmetric. So that's why this dot product can be written as dk dot hk dot dk minus 1. And remember, we want the current d and the previous d to be h orthogonal. So this term is 0. Okay? And let's see why this term is 0 as well. Again, using the equation 5. So earlier there's the equation 5. We have no idea why do we need this. The current d dot product with the next gradient equals to 0. If this one is valid, then it must be valid when k equals to k minus 1. So if you minus 1 on the index, then the previous d dot product with the current gradient must be 0 as well. So this informs that this term equals to 0 as well. With all these effort, we are basically trying to eliminate the entire pink term right here. So now the pink term becomes 0. The entire pink term is 0. Okay, so great. That's why the equation 9 can be rewritten. So equation 9 oh yeah, so basically combine after we handle the upper part of equation 9 and then do a lot of things, we notice that the upper part, the remainder of the upper part equals to this. Basically plug back to equation 9, right? So once you do that, you get this new equation. This is the new beta k, and what's surprising is that the upper part has no Hessian calculation anymore, but it actually brings one a beta k to the bottom, and there is still a hk at the bottom. So now we are going to handle the lower part, the bottom part of beta k. Okay, so we're almost done, halfway there. So let's handle the lower part of beta k in this equation. So basically we have alpha k dk dot hk dot dk. So this is not 0 because only dk dot h dot dk plus 1 is 0, or dk dot hk dot d minus 1 is 0. But if you have dk dot hk dot the current term dk, this is not 0, okay? Because the dk is not hk orthogonal with itself. Okay, so we're going to use equation 6. This is basically when did we do it? I think combination of 1 and 2. Equation 6 here. When we combine 1 and 2, we have this equation 6. Okay. So let's do it. Equation 6 is here again. Now for the equation 6, we're going to pre-multiply dk to equation 6. So basically dk dot the gradient f of k minus k plus 1, and you do that, you do the same thing on the right hand side. So you have dk dot gradient f k plus alpha k dk dot hk dk. Okay, and it turns out you generate the exactly same term of the bottom of equation 10. Okay, so now you know the bottom part of the equation 10 can be rewritten as dk dot gradient f k plus 1 minus dk dot gradient f k. So basically this term minus this term. And here's the current d dot product with the next gradient again. We already proved that's 0. Okay. Now the remainder is this guy. So remainder is this guy. Current d times the dot product with the current gradient. So what do we do then? What do we do with it? We are going to use equation 3. So equation 3 is where we have the definition of moving direction on conjugate gradient and with the introduction of beta. We're going to use this equation. Basically plug in. After you plug in, you have minus the entire term of dk, the replacement of dk, dot with current gradient. So you have all these, and then let's expand everything. Now you will have current gradient dot product with the current gradient minus beta k minus 1 dk minus 1 dot product with the current gradient. Here's the term again. The current gradient, the current direction dot product with the next gradient, that's 0. So the previous direction dot product with the current gradient. that's 0 too. So this one is 0. So this is the remainder. So now you can put it back to beta. Then you end up with this beta. Beta k equals to, on the top, next gradient, dot product with the next gradient, and then over current gradient, dot product with the current gradient. But let's go back to the equation. This is the equation. What's the equation we need? We need the beta k minus 1. So that's minus 1 on the index. So beta k minus 1 equals to, on the top, current gradient dot product with the current gradient over previous gradient dot product with the previous gradient. Done. Finished. Finally finished. So in conjugate gradient, what would be the corrected moving direction? You will have negative gradient plus some multiplier in front of the previous moving direction. But what's the multiplier? So it's beta k minus 1. How do you compute beta k minus 1? You have current gradient dot current gradient over previous gradient dot previous gradient. Or you can compute it in this way. You know, A dot A equals to the length of A squared, right? So you can do the norm of current gradient and then squared, and the norm of the previous gradient and squared. That's the same thing. Okay, that's conjugate gradient method. Now let's talk about the solution process. How do we? Okay, with all the derivations, I don't care. Tell me how to do it. Here's how. Initial gas. K equals to 0, and you have x0. So be aware that we don't need to compute for Haitian at anywhere. Okay? No Haitian. So just compute for the gradient. Now you will formulate this line search equation. Sk plus 1 equals to sk plus alpha k times dk. Alpha k is the step size. We still need the line search procedure to find the step size. However, the dk will be updated by the conjugate gradient direction starting from the second iteration. So what is dk? When k equals to 0, that means the first iteration. We use the negative gradient. So basically, same as steepest descent in the first iteration. Otherwise means that starting from the next iteration, you can have an update. So dk equals to the current gradient plus a pre-multiplier in front of the previous dk, basically dk minus 1. And then on the top is the current gradient, norm, and then square. And then previous gradient, norm, and then square. So that's how you compute for your conjugate direction. So in this procedure, you have no idea what is alpha. So you will perform your sub-problem, small problem for the line search. Find alpha, and then update to alpha. Same as steepest descent. Okay? Then convergence check. If not yet, upgrade, go back to this procedure, and then k equals to k plus 1. Keep on doing this until converge. Okay? That's conjugate. Any questions? No questions? When I was a student, I also didn't know what to ask. And I remember I just saw a magic show. And then the professor told us, okay, go back and do the homework. You will see what happens. So only when I did the homework, And I realized, oh, this is why this is better than steepest descent. Okay, now I'm going to show you by the method. So from last time, I think this is the one. So the node that I used was, let me see which one. Yep. So the one from last year. In today's lecture, I was using the nodes that I used from last year. So you can just download it. So Tajul, maybe you can download it and then repost it, because I noticed you guys are using a new table. So basically just put the same URL for the notes right. Let's see, meta. Okay. This is from last time. Okay. So here I mentioned, okay, this is where we did steepest descent, right? So we now need an update on the moving direction. So because of that, I'm going to create a new variable called d. Earlier we were using so-called, we directly say minus gradient. But for steepest descent, we need to keep a memory of the gradient direction for the entire iteration process. So we cannot just replace the gradient information every time. When we replace it, we have no memory about the previous gradient anymore. So whenever we compute for gradient, let's make it is it a vertical vector? Okay, so let's say it's at the k column. Okay, let's do that. So gradient now will be saved as a matrix, but the k column is the current gradient. Okay. So I did some change here. I changed to I need to save this as a new file. So today is the 17th. So I now keep memory of gradient in all iterations. Okay. What else? I will define a new variable called d. I think I need to do that. So I will say d and k, like this. So definitely d can be negative gradient bracket k. If that's the case, I don't need to have a memory of gradient. I was wrong. Because I need to keep a memory of d, not, do I need? Oh, sorry. No. I need to memorize gradient. because for the beta I need gradient. I also need a memory of D. Okay. So this is new for conjugate gradient. Okay. Now I will remove these words. These are the Newton's method code. I think I will remove them. Let's see. Here, the x alpha needs to be replaced by plus alpha times d. Here will be d. So I will be saying d, the kth d. So this one, this is for conjugate gradient method. Okay? Conjugate gradient method. What else? But starting from the second iteration, my dk needs to have additional terms, the beta and previous d. So here I will say if k is, my code starts with k equals to 1. So if k larger or equals to 2, then I need to do something with dk. Right? So the I already have negative gradient, but I need to have the beta times previous d. So I need beta. So beta basically is some term square over another term square times the previous d. So here k minus 1. So the term right here basically is the norm of the current gradient. So gradient current 1 here over norm of the previous gradient. So k minus 1. Then I updated my dk. Only when k is larger than 2. And what else? Once this is done, here has to be plus and the current d. So this is updating d with conjugate direction information, right? What else? Here are just line search, the same thing. I think I'm done. So let's see. Finish. How many iterations? Initially, k equals to 1. Line search, I used the 1D Newton. Line search, okay, got the solution. Now, in the second iteration, line search 3. Oh, how come not a number? Let me see why. Alpha, not a number. So, DDF. Let's see why it's not. happen when we are in the third iteration. Okay, now. Let's see. F D, because D is 0. D now is 0. So when you plug, oh, okay. So if D is 0, why bother doing line search? So in my code, earlier, no matter what direction that we're doing, we will do the line search. So my code will generate an issue because in the third iteration, D is 0 already. So the alpha term multiply 0. So alpha disappeared. So later on in the line search, the objective function has no alpha. You still take a derivative with respect to alpha. It's nothing. It's 0. 0, and then second order derivative also 0. 0 over 0, that's not a number. That's one. So whenever D is small enough, you don't even need to move on to the line search. I should write a code in such a way. So so my error to prevent this issue, otherwise my code has this issue. Usually I compute for error, let me see where. I compute for an error here. So I should compute error or I would say this is happening only when D is super small. So the equation has no alpha. So we don't even need to do line search if D is 0. So I would say if norm of D equals to 0, or I should say not equals to 0. So if D is not 0, we will do line search. So the entire part right here. Yep. Only when D is not 0. So if D is 0, you don't need to generate alpha. You don't even do line search. But this equation can be outside. And inside. So I will say else. So if the dk equals to 0, then you don't need a, basically there's no line search because dk is 0. If it's super small, we can do line search. But if it's numerically 0, then don't do line search. Your new solution is the same as the previous one. Okay, then do line. Okay. Then this will resolve the issue. So you notice that in the last iteration we didn't even do line search because moving direction is 0. We are already at a very flat area. Okay? So let's have a comparison. Let's open last time. No, this one. Okay. From last time, let's remind you what happened last time. This is steepest descent, right? Let's zoom in. You notice that it's always doing this kind of zigzag. A lot of zigzag. Until the error, this error is so small. Numerically, the error is to the order of, it is smaller than 10 to the power of -3. So I stop. But this time, if we use conjugate gradient, same problem. Okay, you notice that steepest descent, we still, in the first iteration, we still move along this perpendicular direction, and we go down to here, and we didn't make a 90-degree turn because the moving direction was updated, and this update came from so-called beta. And how did we compute for beta? We used a lot of Bayesian calculations. We did a lot of plug-in. And that ensures my current moving direction and the next moving direction is h orthogonal. So why is h orthogonal a good thing? My idea is that Bayesian matrix will transform this elliptical space to the circular space. So when you, after transformation, when you take a gradient, it points at the center directly. That's why it was able to find the direction that moves to the center. But it doesn't tell you how much to move. So we still need the alpha search. So conjugate gradient upgrade the direction, not the left. Okay? The orthogonal, h orthogonal only guarantee after h transformation, they are perpendicular. So originally you are moving down like this, and h orthogonal basically kind of transform the space and allows you to move toward the center, but doesn't know how far. Alpha search helps us how to find the proper step size. Okay. So, any questions? Let me tell you how I'm going to do the exam. I can show you some of my old exam sheets. You need to start practice, because when you are doing the exam, if you haven't tried it at home, you may find it very difficult. And be aware, our grading relies on a huge part is on the exam. So you need to do a good job on the exam. So you can already solve these. So basically, this is what I gave my students in the past. Okay, there's an optimization problem. with a bunch of coefficients. Initial guess is ABC, CBA. So what are ABCD? Earlier I gave a list to the students. Okay, if you're this person, your ABC is this. If you're this person, your ABC is this. Okay, this is what I did. So no one will have this exactly same problem. And I will tell you, okay, start the iteration with k equals to 0. The criteria is whether the iteration reaches reaches 4, or if the accuracy is 10 to the power of -4. Either one satisfied, then stop. And for the line search, I specified you need to do 1D Newton's method. Write down the solution process, solve by Stephenson conjugate gradient. And for this year, I need you to solve with Newton's method as well, because we have a big exam. Okay. I guess this is already taking you a lot of time. So I may reduce the amount of iteration. I may say, okay, solve up to 3rd iteration. Don't do the 4th one. Because for line search, it's taking a lot of time. Okay? So similar kind of problem. Please go home, practice by yourself. I'm giving you MATLAB codes. You can compare with the codes. Supposedly, by hand, you may not have enough accuracy, but that's fine. The values should be similar to the results from the code. And now, it's a good time for you to practice. Let's check on the course schedule. Today's yep. So we are on track. These already done. And 3 weeks from now, we have a meeting. 40 points, a lot of points. Next week, we are going to move on to constrained optimization. For unconstrained optimization, we are only learning 3 different methods. There are more in the literature, in the textbook. If you're interested in the future, go figure out. But in my lecturing, I will only cover Newton's, Stephenson, and conjugate gradient. Okay. And next time, for the constraint optimization, we will start with the simplest problem. It's called linear programming. Okay. Linear programming is completely different from, the procedure is completely different from what we have learned so far. And a week later, we will talk about so-called projective programming. The derivation of projective programming is very, the feeling of learning from today, for QP, you will have the same feeling. A lot of derivations. Okay, where are you going? Okay. But it's also a very important method. But having exams on KKT and QP may be difficult, because we have only 3 hours. I don't think you have enough time. So either I reduce the complexity of problem, or I will pick up something in the exam. I will reduce the difficulty. Okay, but be aware, I'm still deciding whether I will include LP and KKT in the exam. Definitely not QP. QP is too large. Okay, LP and KKT possible. So any questions? If not, I can quickly just check everyone's attendance. So Ben is here. 换中 okay. Kelvin. Try. Are you taking the course second time? You can do that?
Because first time was in my bachelor degree, and
You can do that.
yeah, but like I cannot.
So you are expecting to get an A plus?
Not really.
Okay. Jerry. So 右滑 Forwards? Oh yeah. 运动。Jump. Ray. No. Ray. No. This is Okay. Okay. Ballroom. Okay. Sit. Sit. Here. Okay. This is Rick. This is Rick. 思桥。As in here. 议程。Okay. Ping. And listen. 右加。Okay, everyone's here. So, any questions? Probably you have no idea how to ask questions. I had the same feeling like you, but I can show you one of my students' thesis. He is using conjugate gradient. So let me, since we have a lot of time. Let's see his name. Sorry, in Chinese. Okay, so we are doing basically what you are doing right now. Okay, it's a robotic problem. So there's a robot moving from one direction to another direction, but on the way there's an obstacle. So we will use simulation to figure out, oh, it's gonna crash into this obstacle and then penetrate through and then get out of the obstacle. Okay, so there's a certain portion on the way that is like a danger zone, right? So basically, he defines certain intermediate positions inside the danger zone. We perform optimization to find safer positions. So later on, you can move up to here, then move to newer places, and then continue to its original mission. So, but how do you get this? How do you get this new trajectory that is not hitting the obstacle? So basically, for every replacement, it's based on optimization. So what we did was, you of course can do this super safe, but it's not efficient. Why did you move so far away? You can just move with a certain gap. That would be the most effective way. That's why the original design point is somewhere inside close to the obstacle. So maybe we can move to somewhere on the top. But the new point is close to the original. So the objective function is we want to minimize the new design point and the original. So numerically, it's like trying to move the design point to the original position. Why do we do that? If we do that, then the original position is the solution, but it's gonna crash into the obstacle. So if you only have this objective function, it's not enough. You need constraint function. So what's the constraint function? The constraint function is the new point cannot crash into the obstacle. So with that constraint, you can only move surround the surrounding area of the obstacle. Those are possible solutions. None of them will crash into the obstacle, but there's one position that is closest to the original one. That's the objective. That's the objective function. Okay, so I will show you how we formulate. Let's see. Conjugate gradient. This is what you learned today. Yeah. So basically, minimize the robot position minus the original position. So basically, shorten this distance. Shorten this distance. But we found that sometimes if you move your design point here, and there's no control of the design point. They could be everywhere, as long as this distance is small. So we add newer terms. We try to, I always imagine these as magnet. It's like you're putting a magnet at the original position. And there's a pulling force. Your design point is being pulled closer to the original point, but not hitting the obstacle. Okay? And if you have this numerical magnet between each other, then this numerical magnet will control, form a chain of motions numerically. That's why you have these distance to be minimized as well at the same time. So we basically minimize a lot of terms. But meanwhile, what's the constraint? Constraint is we define something called danger factor. The danger factor needs to be, this is wrong. Shouldn't be like this. Must be smaller than or equal to. So anyway, danger factor makes sure it doesn't bump into the obstacle. Okay, and there are many tricks I never talk about in the course yet. We will talk about it. But eventually, you see in this person's thesis, he derived a lot of gradient because he's trying to use Newton's method. This is the Hessian matrix. Okay? So if you, in your own research, if one day you realize you can formulate optimization problems, you can try to solve it by what you learn in the class. If it's an unconstrained problem, you can use Newton's steepest descent or conjugate. Okay? So this is what it is. So let me just show you some results. So it's like he simulated a robot, just like what I did in front of him. And there is a red spherical ball, which is the obstacle. Okay. So originally the robot motions is gonna collide with the ball. So he highlighted multiple snapshots of the robot configurations by the yellow color. So these robot positions are the bad ones. So he performed optimization, blah, 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 and he found, okay, you can do this. So every position is determined by conjugate gradient. Okay? And if the ball is moving, the computers will update. Okay, the ball is moving. Okay, let's solve optimization again. So he showed how you can dynamically avoid the obstacle. Let's see here. Not this one. The dynamic one. No, not these. I just want to show you the dynamic motion. Yeah. So originally, if the obstacle is not changing its position, you should be able to see like a smooth curve, which moves around the obstacle. But in this practice, the spherical obstacle change its position. So even the safe curve is no longer safe. So he performed a second round of optimization. So you will see several peaks, several curves. That's mainly because the obstacle is moving. So this is like an initially, and then what? Okay, you can see obstacle move is a position. So the safer trajectory is like this, and then the object is keep on moving toward the trajectory. So the robot will escape like this. Okay, he intentionally asked the obstacle to move closer to the robot, so it becomes a dangerous situation. But just to show his algorithm is able to keep on doing optimization to avoid collision, something like this. Okay. So that's what his thesis was about. So there's already 1, 2, 3, and this person 4, and there's a 5th student right there doing the exact same problem, but they try different algorithms. So this is Newton's method, steepest descent, conjugate gradient. Okay. Okay. Just for your reference. I think I have a good progress today. So I finished early. Anything you want to ask before you go? No? We're good? Okay? So that's it for today. Thank you. Bye-bye.